Yeah, I just stick this somewhere, like anywhere, like I can. So it's not in the. Put it over here. It's okay that you don't have to see it. Okay, as long as you're in.
Some fathers are good, but I'm scared getting to be like long hair. Like, I don't know. Yeah, I think I'm gonna want to be. So I want to yeah, set it up. Yeah. Whether you want to spin it or I think that's yeah. Well, say more maybe. Yeah, I think so. I have some books actually that I can share that for like, so let's see. Oh, she went. If you're so straight, yeah. Well, I think that's what you do. It's still. Yeah, a bit low.
To call out and let me know that, right? But anyway, let's get started. Let's get started, but let's turn the volume down a smidge because there we go. That's better. Okay, so up until now, wait, no, last reminder. Next Wednesday, exam coming up. Exam is over everything, including this week. So I strongly suggest prepare thyself. All of a week from today is dedicated to review. There are a fair number of skills we've done and practiced. I strongly encourage you, yes, you, to think about what do you need? What are you bad at? Not only should you review that till now, but a week from now, what you're still bad at, ask in class. I will answer questions galore based on what you need. Okay. Think about that. But today and Wednesday of this week, we have a smidgen more material to cover. We have been talking about how things move, describing describing motion, putting motion to precise mathematical terms, and exploring the consequences of if you know this, what can you find about that? But all of this has been effects. We haven't talked about causes one bit. And just being able to describe what something is doing is not physics. Really all we've been doing is mathematics. Now we're going to put the physics to it. We're going to attach cause to effect. And the cause of motion, actually that's a bad way to put it, as I'll explain in a second. The causes of motion is called force. So today we are going to have an introduction to force, or if you want to be all fancy pants about it, we will say dynamics is the study, the science, the branch of physics.
Josh, can you help us set it up? Sir? Rachel, would you prefer a time lapse from the back of the chair styling to the time angle, or a back of the chair?
Dynamics is the study of interactions, the study of forces.
When it's dry, so you need to use this.
Forces are interactions.
You were looking at my face then, because I'm not.
So here's the big deal.
What drives me nuts?
Things push on other things. We will, in the study of dynamics, be able to, our goal is to be able to calculate what that does to an object's motion. And from what we have been doing for the last since the beginning of the semester, once you know, as it turns out, the acceleration of the object, you should be able to calculate any other quantity of interest. If I ask you about the position of the object at some time, the velocity of the object at some time, how long it takes to blah, 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 you should be able to use the current skills to get there. But still, our goal is to now introduce the nature and the nature of interactions. And again, I'm going to say that these are the causes of motion. Let me put that in big quotes because, as I will say in a second, it's a little more sophisticated than force causes motion. So here's the top level. We have a couple of definitions. I'm going to define the following terms: mass, force, and inertia.
Yeah, I love that. Yes.
Yeah, those are my three big ones.
That wet frizz gone. Nice, hydrated, shiny looking curls are starting to form. Now I'm gonna run through this in sections.
Mass, measured in kilos. I should say kilograms.
Most of all, speed.
Most of all, speed.
And I think we're going like why are so good for speed? Like it covers everything.
So that's a good thing.
Like.
And I'm going to describe this as quantity
All right, so I think we should like lean into it.
of a substance.
Why so?
Ultimately, if you know how many atoms there are, you can multiply how much each molecule masses with the number of molecules, and you get the mass of that object. Mass is truly unchangeable in our course from the perspective of classical mechanics. Einstein discovered exceptions. Mass is, for our purposes, unchangeable. And everything that we're going to deal with has some amount of mass. Light things have small mass, heavy things have big mass. Mass is different from weight. We'll talk about weight in a little bit. Weight, pounds, weight measures how hard a planet pulls on some amount of mass. So mass is the amount of stuff itself, and weight is the force exerted on that mass. More on weight in a second. But I did want you to distinguish that this is not, mass is not the same as weight, even though it is related. Okay, force, I'm going to define force. It is measured in kilos, measured in newtons.
Elasticity.
I can't say that. I can't.
I'm going to say this is the strength of a push or a pull.
Bounce back.
Without
Bounce
weight,
and shake.
it's fines without.
It's the ship spray.
That probably should, yes, right, that's gonna pull our. That's what happens.
I will also point out, let me just draw it on here, force is a vector. You can have a leftward force and a rightward force, an upward force and a downward force. Super important.
Oh my gosh.
You can have a positive force and a negative force. And that's really important because, as it'll happen in a lot of cases, total force will be zero. For instance, this bowling ball right now has a positive force. The table is supporting it upward, and the planet, is pulling it downward. Positive and negative balance out. Total force is zero. Inertia, I'm going to define as opposition to changes in velocity. Opposition to change in velocity. Today is a top-level view of dynamics, a first picture. We're going to spend like a month getting deeper and deeper and more sophisticated and solving problems and investigating scenarios and getting jiggy with it for lots of different forces, lots of different scenarios. But where do we start? I'm going to say we need to start with Newton's laws, the foundation of mechanics, the foundation of dynamics. So let me lay them out. I want you to forget everything you've learned about Newton's laws in the past, because in my experience, the way that grade school teachers teach Newton's laws, the words that they use, they're more or less a direct translation of the Latin that Newton wrote in. That translation is bad It gives rise to misconceptions.
And
Here is something where I will test you on. Here's something where I test you, and I will be very picky. I will ask you, how did I teach you Newton's second law? How did I teach you Newton's first law? And you need to be able to spit back. It'll be multiple choice, but you need to be able to identify how I explained it instead of how you may have learned it in grade school, okay? You've been warned. Okay, so I am going to explain Newton's first law, N1L, avoid some things, as everything, forget about object in rest, object in motion, blah, 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 with mass has inertia. Everything with mass, and that's everything we're going to deal with in this class. Everything you can point to, anything you can lick, even in principle, has mass. Everything with mass has an opposition, a resistance, fights against its velocity changing. Eh. So for instance, here's something with a bit of mass. Yeah, here's a bowling ball that I bought from Goodwill some time ago. And I'm going to say, just sitting there, to the extent that I don't interact with it, if I don't exert a push or a pull on it, it's going to stay sitting there. It does not like to change its velocity. Now let's give it some velocity. I'm going to interact with it. Look, I am not kicking it and it's still moving. Oh, it slows down a little bit as friction acts on it. But for the most part, you know, if I want to change its motion, if I want to accelerate it, I've got to interact with it. I've got to exert a force on it. Another example. You're driving down the freeway. You take your foot off the gas pedal. Does your car instantaneously stop, come to rest? Well, mine does, but that's because I drive a piece of crap. Yeah. Okay, so no, you don't need force to have motion. You need force to change motion. And your car has an inertia, has a tendency to avoid instantaneously going to zero velocity or really to any other velocity. It tries to keep, to the extent possible, it resists changes to velocity. It takes a gas pedal or the air drag or a brake pedal to stop it. If you don't believe me, have the car move at 1 mile per hour, stick your foot out, and see if the car is instantaneously going to stop when there's no force on it. Don't do that. Okay, so I claim Newton's first law. How I want you to describe it, to know it, is that everything with mass, which is everything we talk about, has inertia, resists changes to motion. And the example, one of the examples I just gave, is a car on the highway. Doesn't just stop when you release the gas pedal. A long time ago, before Newton came along, well, actually, Newton's first law wasn't discovered by Newton. It was discovered by Galileo. Newton synthesized, put things together and made a coherent whole of them. But before Galileo, there was a very clever man called Aristotle, and he wrote the first book. It was called, the first physics book, it was called Physics. In Greek, I can't pronounce the actual title, but it was called Physics. And in it, he proposed that, you know, imagine pushing a heavy cart across a field. If you push hard, it goes fast. If you push gently, it goes slow, right? He proposed that force causes motion, causes velocity. Well, Galileo was clever. He realized that the nature of motion is not wanting to be still, of pushing a cart across a field. That field is interacting with the cart. It's exerting a force. It is exerting a push or a pull on the cart. The true nature of motion, to the extent that you can reduce friction and interaction, a force on an object, to the extent that you can minimize that and just study one thing at a time, the motion of the object instead of the interactions with the object, motion just likes to stay steady, doesn't seek zero. Another example, does the moon have rockets on its butt? Is the moon crashing into the Earth? The moon has been orbiting for 4 billion years without a force continuing to push it around the Earth. It doesn't need something to push it around. It's going around nice and steadily, very happily. There is no force needed to keep a steady velocity. You need a force to change its motion. If you put rocket on the moon's butt, you would accelerate it. Oh, let's not do that. Okay. So far, so obvious. And Newton's second law. Newton's second law tells us, all right, so by default, things don't change their velocity. Well, when do things change their velocity? Newton's second law, N2L, to change a motion, change an object's motion, to change an object's, to be precise, velocity, or that is, to accelerate the object, remember, anytime velocity changes, delta v, the upstairs of acceleration, is non-zero. If you have a velocity which is not constant, you must have or have had an acceleration sometime. Likewise, if you have an acceleration, an object cannot have a constant velocity. Okay. Anyway, to accelerate an object, to change its velocity, one must apply unbalanced oh, for God's sake, unbalanced or net force. Right now, there's a force on the bowling ball, right? The Earth is gravitating it. The gravity doesn't go away just because it's sitting still, right? But the floor is supporting him. The floor is supporting that bowling ball. There are two forces, one plus force, one minus force. What's the total? Zero, right? Those up and down forces cancel, so the bowling ball doesn't have a net force. Okay? If I take away the force that the ground is exerting, say by throwing it through the air, you better believe his motion will change. When there's only one force acting on it, what's its acceleration? What is the acceleration of an object that only has its weight acting? Negative 9.8 meters per second squared. It accelerates at negative g meters per second squared. Yeah? Deja vu? Okay, so Professor has lost his pen. Oh my goodness, I'm such a loser. Okay, to find the magnitude of the acceleration vector, the acceleration is given by the equation. This is the core of the next month, maybe month and a half. I need to look at the calendar of class. Beware. It is very common for students to screw up one term in particular. Math is easy peasy. I'll usually just tell you a math, okay? Catholics have an advantage on here, but everyone usually gets math. The problem that people most commonly screw up with is F net. I will give you a force and ask you for an acceleration. You will plug in the force I gave you, and you will get it wrong if that force is not the only force acting. I will tell you I have a weight force acting on me of 600 newtons. What's my acceleration? Look at me. Am I accelerating? My weight force is not the only force on me. It is not the total force on me. Look at me right now. Am I accelerating? No way. My total force is 0. There are two things pushing on me. Ground supporting me, positive force. Gravity pulling me downward, negative 600 newtons. Okay. Now, if I take away the ground, I don't know, the way today's been going, maybe I shouldn't take this risk. If I no longer interact with the ground for a few milliseconds, then what happens? Do I have a net force now? Sure. And when one force was acting on me, those 600 newtons, 600 odd newtons, probably more like 700 after that Starbucks run, 700 odd newtons gave me an acceleration. I want to emphasize this is a vector equation. So if you want to know the direction that you accelerate, that direction of the acceleration is the same as the direction of the net force. That might seem obvious, but trust me, sometimes this will pop up and be weird. If I tell you that an object is moving up and slowing down, which direction? Point for me, point. An object is moving upward and slowing down. Which direction is its acceleration? Everyone point. Which direction is accelerating that's moving up but slowing down? This is the correct answer. Do you think that the negative force or forces on it are bigger, or the positive force or forces on it is bigger? A is this way. Which direction wins? The up forces or the down forces? The down forces. The total force is negative if the acceleration is negative. Follow-up example. Turn to your neighbor and discuss for a second. I've been talking too long without a break. An object is moving down and also slowing down. An elevator is going from a high floor to a lower floor and about to come to a stop. Which is bigger force on someone standing in the elevator? The force that the floor of the elevator exerts upward on them, or the fact that the gravity weight force is still pulling them down? Turn to your neighbor and discuss. 2 seconds. Which wins? There's less down than it was or just keep going down, right? Or it's like okie dokie. Real fast. Which way does the floor push on me? Does the floor push me up or down? Point. Point. Let me see the whole class. Does the floor push me up? Or does the floor pull me down? Yeah, right? Which way does the earth push or pull on me? Yeah, big shocker there, right? Which of those wins? Tell me this, which way do I accelerate? Up or down? Nobody? Come on, we've been studying this for like a month. Which way do we accelerate? I'm moving down and slowing down. What is that acceleration? Draw a graph. Draw a graph. Draw a graph, my friends. Elevator going down and slowing down. That's not negative acceleration. Negative velocities going down and slowing down, approaching the horizontal axis. That's an upward acceleration. Negative 5 meters per second, aiming towards 0 meters per second. Am I going down or am I going up? I have to add a number to negative 5 in order to get to 0. Positive change, positive acceleration, yeah? Yeah? Okay, so, which direction am I accelerating if I'm moving down and slowing down? Show me with your hands. Everyone, show me with your hands. What did I just tell you 2 seconds ago? Okay, up. Which force wins, floor or planet? Which force is up? The floor supporting me, pushing me upward. I feel like there's extra pressure in my feet when I'm going down and coming to a halt, right? Everyone's been in an elevator, gone down, slowed down. Don't you feel heavy? The ground is pushing on your feet. That's the feeling of accelerating upward because the force on your feet is bigger than it normally is. No, you don't like that. Lots of blank looks. Question me, Dahlia. Yami.
Where the elevator goes too fast down and like it turns into a pancake, would that mean that the force of down is stronger than the?
It's not the downward velocity that turns you to a pancake, it's the stop at the end. And yes, what causes you to pancake there is a force squishing you, not downward. Gravity doesn't get stronger because you're in an elevator. The thing that squishes you is the floor of the elevator pushing you up to pancake you. I mean, it's the elevator that's stopping you, right? The planet isn't stopping you. It's the floor of the elevator pushing up on you that brings you to rest. I got a lot of blank stares or a lot of wrongo answers. Turn to your neighbor and discuss for a second. Moving downward and slowing down, the floor is bigger than the planet weight force. Discuss. 2 seconds. Now ask me a question. See how this all builds on itself? If the first part, if finding the acceleration direction is still hard, then you need to resolve this before the test, before we move on immediately. So ask, question me. What does the sign of velocity tell you? The direction of motion is velocity, not acceleration. Acceleration does not tell you the direction of motion. Maybe graphs suck. How about a table interpretation for this? Let me ask you for velocity versus time. If we are moving downward quickly, give me an initial velocity, moving downward quickly. 3. 3? 3 is not down. -3. You're moving down, moving negative direction. At time 0. At time 1, how fast am I moving? I'm slowing down while still moving down. Give me another velocity. Negative what? -2, sure, why not? At 1 second, I'm moving downward at I'm moving downward at 2 meters per second. My velocity is -2 meters per second. Do you feel okay that this is a slowing velocity? My magnitude is getting closer to 0, yeah, and it is moving in the negative direction? Riddle me this, Batman. If this is my initial and this is my final, what is delta V? Calculate for me. Ready, set, go. This would be in a Google form thing if I could possibly Google form it. If I could see Google. I'll tell you the downstairs is 1. Oh, I'm so smart. Turn to your neighbor, check each other. All we're doing is subtraction here. Check your subtraction. Ready, set, go. Who says -5? Okay, let's practice. Let's do this. My final value, -2, minus my initial value, -3. If I'm $2 in the hole, and then somebody relieves me of $3 of debt, how much money do I got? You owe me $2. I forgive you of $3 worth of debt. What have I done? How much do you got? How do I subtract a negative number again? Add it. What's -2 plus 3? 1. It goes by the same name as 3 minus 2. 3, yeah, 3 minus 2. For God's sake, I can't write. Right? What is my acceleration? Positive or negative? 1 over 1 is a positive number. How am I changing my velocity? The change from a more negative to a less negative number. Which direction on the number line am I going? From a more negative number to a less negative number. Which direction am I moving? Positive direction. So moving downward, negative velocities that get less negative, slow down. That's a positive acceleration. Another example, give me a kick, or give the ball a kick. I'm going to exert a force to slow this ball down. Somewhat of a force, okay. Which direction did I push on the ball? It was moving to the, from your perspective, that's right. And then it wasn't moving to the right. It slowed its rightward motion. Which direction is that acceleration? Point for me, point. If you are moving right and then you aren't, which direction are you accelerating? Left, negative direction. Yeah, you betcha. Okay, so tell me, if that's the direction of the acceleration, what was the direction of my force? This should not be difficult. If I give you that the acceleration is to the left, where's the page? If the acceleration is in the negative direction, you should be able to identify the direction of the force. Which way did I have to push on it? Which side of the ball did my foot go on? Didn't I push this way on the ball? I didn't kick it further. If I kicked it further, I would have turned a positive velocity into a bigger positive velocity. I would have done a change and acceleration that way. If I push on that side of the ball, I'm getting it going faster that way. The direction of the force is equal to the direction of the acceleration. Vectors always point in the same direction. No, that part, to say that if it accelerated left, the force was left, that was not supposed to be a tricky part. Did you guys just have an OChem test or something that I don't know about? That happens from time to time. I get a lot of exhausted, dead look in your eyes, and it turns out not to be me. I'm going to, God, I wish I could Google form ask for questions. Turn to your neighbor, discuss for a second, and then I'd really appreciate it if someone would give me some feedback, give me a question or two. Where does that go? Please discuss with your neighbor, then rat on them and tell me what they're confused about, eh? Review what we just talked about, the whole section. Half a second, Isabel. Let me wait until everyone can hear you. 10 seconds. Help me out. Isabella, you had a thought? Shout it out loud for everyone. Sure, absolutely. Which direction do I have to kick a ball to get it to move to the left? If I kick it left, I'm exerting a leftward net force. What's the sign of the acceleration? From the usual right-left coordinate system, negative is left. Which direction is my force? When I kick it, I'm pushing which direction on it? Left. What if you got, sometimes this happens in sport ball, I've been told, you get two people kicking on the ball at the same time. Suppose Sahu, let's not do this because I'm going to stub my toe so hard. Suppose Sahu comes over here, and I heard he worked out once. You can guess for me. He kicks right, exerts a big force. I, with my scrawny little professor legs, kick left. Which direction is the ball going to accelerate? To the right. If you got a bigger positive force than negative force, the net force is going to be positive one wins. It's going to accelerate to the right. Better? Dahlia. Yami. It's her D&D character.
Like the floor. You said that if you were to kick it to the right, it stopped because it reached the force from the left, and that's why it's stuck. That's where I got stuck. I was confused. I'm confusing the force that accelerates it with the force that stops it.
But acceleration, stopping, I should say, stopping is an acceleration. Any change in velocity, speeding up or slowing down, is an acceleration. If I slow down, that means I'm accelerating against its velocity. Negative number getting less negative, positive number getting less positive. Other question? You know, if this stuff were obvious, it wouldn't have taken really bright brains 2,000 years to figure it out. Aristotle's physics lasted about 2,000 years before Galileo Newton figured out he was wrongo. So I do want to emphasize something here. If this seems strange, confusing, hard, difficult, you're not wrong. It is hard to wrap your brain around at first, but I promise you it gets easier. But it doesn't get easier if you just wait and let it wash over you. You got to engage with me. I mean, I'm already married, but engage with the subject. Mitzi.
So the force is greater going from left to right, and then you try to stop it, but let's say it keeps moving. That force is positive, even though you have a negative force against it.
Thought he was kicking it at the same time. We both arrive at the ball at the same time. His positive force is bigger than mine. I mean, seriously, look at these lines. His positive force is bigger than mine. So the net force is positive. Positive, big positive plus a little negative is a positive number. So the acceleration is positive, rightward. Saki wins. Then there will be two accelerations. The first acceleration will be positive because there's a positive force. Saki was kicking it right. The second acceleration, I am kicking it left. I am trying to oppose its rightward motion. How do you oppose a positive with a negative? I accelerate it in the negative direction to slow its positive down. It's positive velocity. Does that help? Hello? Still weird. Still weird. You still don't like it. Keep asking.
As the ball falling, to get it back up into the air, you have to apply a greater amount of force on the ball. You know, if you just have the leg but they're just gonna keep going through because you're not opposing a big.
I like that. How do you turn a down into an up? Don't you have to push up on something that's going down to move it up? What direction are you pushing on the volleyball with your arms? What direction is its acceleration? It goes from downward velocity to upward velocity. That's a big positive change. Yeah, please, Isabella. Sure. Don't you have to, yeah, if you're, what's that called? Spiking it? You push down so that it's hard to get, right? You strike it forward and down, or I guess from its perspective, backwards and down. Okay, so if its initial velocity in some direction is 0, to get it moving in that direction, you have to accelerate in that direction. You have to push it in that direction. Change its velocity with an acceleration. I like it. Okay, let's move forward. And I will happily come back to these points to continue to move your brains forward into it. But I would like to get some things down. Okay, now Newton's second and first law tell us the nature of how force causes a change in velocity, changes motion. However, the third law is different. The third law doesn't talk about cause and effect. The third law tells us more about the nature of force. The third law is by far the hardest law for students to learn. In my experience, what I've seen is so many more mistakes about the third law than the first and seconds combined. So I'm going to give a lead up to Newton's third law. First off, first point, and I hope that this is obvious, you can't push on yourself. Right? I mean, think about it. Think about it. Let me try to disprove this. If I disprove this, I can fly. Oh, I'm pulling up on my foot, but I'm not flying. Yeah? Do you all agree I didn't fly? I tried to exert an upward force on my foot, but my foot was pushing down on my hands. Balanced, no total change. I'm not saying you can't push on yourself at all. I'm pushing left on right, right on left. I can even move my body around. But by doing this, I can't accelerate myself that way or that way. Right? You can twist and stretch and compress your body, but you can't move where you are. You can't move your center of mass. Every force So point 2 here, every force reflects an interaction, represents an interaction, reflects an interaction between exactly two objects. There are two things interacting in every force. That doesn't mean that each thing feels two forces. It means that each force affects two things. Objects. The other big goof here, the thing that I see year after year, is an object. To be an object, it must be possible, in principle, this is the technical definition. Think hard about it and you'll understand it. To be licked. It's not an object if you can't, in principle, lick it. The ground, the table, the planet as a whole, a star. Don't lick stars. Very bad for your health to go over to the sun and lick it. Let's practice identifying pairs of objects real fast. Pairs of objects. I kick a ball. What are the two objects? Talk to your neighbor real fast. I kick a ball. What are the two objects interacting? I kick the ball. The interaction is the kick. Okay, hopefully you said the professor and the ball. That's not to say the planet isn't gravitating the ball. It's not to say that the ground isn't supporting the ball. Those are other forces that act on the ball. But if I'm thinking about the kick, that's an interaction between me and ball. Does the ground participate in the kick itself? No. Okay, can you lick the ball? Can you lick me? I mean, no, don't, but in principle you could. Next example, a ship is floating on the ocean. For Arizona natives, the ocean is a big pool of water that is not here, okay? Okay, anyway, a ship is floating on the ocean. What two objects are interacting? Turn to your neighbor, discuss real fast. All right. What else is interacting with the boat? The water. If anyone says buoyancy, I challenge you for your entire grade to go out and lick the concept of buoyancy. Buoyancy is not a thing. Buoyancy is the chapter title of section 15.6 or something. You must be able to lick it. Boat and water are the two things interacting. My Earth pulls me down. Earth pulls me down. That's my weight force. Gravitationally pulls me down. Identify, turn to your neighbor and discuss. What is the third law? What are the two objects interacting? The two objects interacting in my weight. Time's up. Anybody who said gravity, anybody who said gravity is the other object, me and gravity, no, do not pass go, do not collect $200, go directly to jail. Gravity is not what you can lick. What object, without which object would I no longer be pulled? The planet as itself. By the way, very important, take a note for this, take a note for this. There is a difference between the floor and the planet. If I put this classroom in outer space, I would not stick to the floor. Right? Duh, yeah. Everyone's been to outer space and knows this? Well, trust me. If this floor collapsed, my weight would not disappear. I would, in fact, accelerate downward at 9.8 meters per second squared. I distinguish, sure, the floor is part of the planet, but what causes weight force is the entire 6 times 10 to the 28 kilograms of the planet. What causes the support force of the floor on me is this, it's probably a couple of tons of material, but still, these couple of tons of flooring that ASU built. There's a difference between ASU and the entire planet. Don't tell Michael Crow I said that. Is good? Is good? Newton's third law. You are now ready for me to lay down the law. Every force acts twice. That is to say, in other words, every time two objects interact, exchange a force, each object fells, oh, for dog's sake, feels the force. These are the same force felt from opposite perspectives, felt from two perspectives, felt from different perspectives. The strength is the same and the direction is opposite. Strength is equal. The direction is opposite. Really, the first 3 lines are the same thing said 3 different ways. Pick your favorite. Hmm? You need a neighbor. Scooch over, get a neighbor. You can turn around if you want, but I want everyone to do this experimentally. We're going to test Newton's third law. Let's try to falsify it. I want you to high five your neighbor, but only let one of you feel it. Only one of your palms is allowed to sting. Ready, set, go. Figure it out. Can you get one palm to sting, but the other be nothing? Not here. Do you both feel it? The test is, do you both feel the force? Do both hands sting? If both people don't feel the clap, then one of you needs to go to the neurologist. Okay, I'm gonna test this myself in a couple of ways. Yep, both hands. And it doesn't matter, by the way, that they come to rest, that they're both moving equally. I can move them to overcome. I can have one hand be still and the other hand slap it. I can really keep one hand from moving. No matter what you do, you cannot break this law. Both hands, to the extent that you don't have nerve problems, will feel the clap. Question? The third law says if the air turbulencifies the aircraft, then the aircraft also pushes back on the air. But I haven't been air, at least recently, so I don't know if that helps me feel it. Okay, so consider the people on the airplane jostles up and down. When you bump up and down on your seats or maybe hit your head on the cabin, what's this called? Ceiling, then the airplane itself also recoils a little bit. Now, the airplane is much more massive than you are, except for your mama. So its acceleration is proportionally less. Go back to A equals F over M. Same force gets different accelerations if the mass is different. So the airplane does recoil a little bit when you bounce on it. Hey, who shot a gun before? Okay. Is there such thing as an absolutely recoilless gun? It takes a lot of technology, gun technology, to reduce recoil. Every time you propel a bullet that way, the gun is pushed back that way. Every single time. Every single time. Let me ask you this. I'm going to step off this chair. If you don't listen, I'm going to step off this chair. The earth is going to exert a force on me. Okay? I will tell you, as before, the gravitational force that my belly causes me to have is about 700 odd newtons. Back to 600 after I've burned all the calories from this lecture, whatever. And I want you to turn to your neighbor and tell each other, does the earth feel a force from me? Ready, set, go. Turn to each other.
Yeah, yeah. That's all. But he's pushing on hard.
Not the landing. When I'm in the air, is the earth pulled up? Not the landing. I'm not talking about landing. While I'm in the air, earth pulls me down. Do I pull upward weight-wise? Do I gravitate upward? The answer is yes. Yes. Now, how hard do I gravitate upward? Earth pulls me down with 600 newtons. Do you think that the force that I exert on the earth is measurable? Is it bigger than 600? Less than? Discuss with each other real fast. What do you think the strength of that force is? How hard do I gravitate the earth? Oh, for dog's sake. Oh, for dog's sake. Back, foul beast. Oh, for God's sake, I'm trying to make a point here, and it's not helping. Everything is ruined. Life is awful. This sucks. I suck. Ugh. Strength is equal. If the earth pulls me down with 600 newtons, I pull up on the earth. It's not just yo mama, it's everyone. You gravitate up on the earth as well. What's the mass of the earth? Small, big, really big? The earth is really freaking big. So the medium size 600, 700 Newton force that I apply to the earth causes basically jack acceleration. No acceleration, no measurable, conceivably measurable acceleration. The acceleration of me, what is it? 10 meters per second squared, 9.8 meters per second squared downward. The acceleration of the earth, 9 times 10 to the minus 33. 0, 32 zeros, and then a 9 meters per second squared. You'll never actually ever observe that. You'll never measure that. But, if the earth pulls me, I pull the earth. That will be a test question. Think about it. Think about it. Actually, every single object in the universe exerts a gravitational push or pull on everything else. The total force, by the way, the total force between the objects depends on the two masses multiplied together. Earth is really honkin' big. I am astronomically small. Those two numbers multiply up to give a medium-sized number, 600. The Earth is really big. The moon is also really big. You know what the moon does to the Earth as it gravitates? Causes tides. Yeah, that's a rather big interaction. Tides are rather a lot of water. No, that way is bad. Turn to your classmate. You are not attracted to them because both of your masses are relatively small, at least gravitationally. Okay, so gravity, I think there's a famous quote that probably actually isn't real. There's a famous fake quote probably that says gravity is not the force that brings people in love or something. It's attributed to Einstein. I don't think it's actually real. Okay, so again, two objects push at each other, the strength is equal. That doesn't mean the effect is equal, right? The force is not the same thing as the acceleration. Almost done. I mean, good thing we're almost done because we're almost out of time. Hey, shush. I run, I Kramer to a halt on a rug. Which direction is my acceleration? I was moving this way, now I'm not. Point to me the direction of the acceleration. Again, I was moving this way, shh, come to a rest. Which direction is my acceleration? A change from this to zero, from your perspective, positive becomes zero is a negative change. Which direction do I make the rug skid? The rug skids this way, right? So which direction do I exert a force on the rug? If the rug pushes me that way, I push the rug that way. The directions are opposite. It can be weird to think about the floor exerting a force on you, you exerting a force on the floor. I encourage you, whenever I give you a problem like this, imagine a rug on a smooth floor and think what happens to the rug. You do push on the floor. I am pushing on the floor. Actually, for that matter, I'm not skidding, but I'm pushing on the floor right now. Not just vertically, horizontally. If there were no friction between me and the floor, I would be moonwalking like crazy. I could move my legs, but if there were no sideways force, it is the floor that pushes me around as I walk. It is the floor that pushes you. To test this hypothesis, go to an ice skating rink and while keeping your skates straight, try to move. You're not going to do it for the most part. You minimize friction and you're not going to be able to just push that direction. You got to do fancy pants skating to actually move. Okay, we're almost done. As I said, let me give you a formula. Zoom out. Again, I want to distinguish. What's mass tell you? How much of something there is. What's weight tell you? How hard it's pulled. Remember that. Write that down. That'll be a test question. You need to be able to distinguish. Mass is an amount of stuff, ultimately counted up. Weight is how hard that stuff is pulled. Go into deep space, you still have inertia. In outer space, you still have inertia, even though there's no planet pulling you to it. Okay? Weight depends on having a planet or a star nearby, or a moon. Weight depends on there being something to gravitate you. You still have mass in outer space. You can't accelerate to the speed of light with just a flick in outer space. Okay. The formula for weight is mass times, what's this called? Not gravity. What do I want you to call this? It's the field, gravitational field. Mass times gravitational field strength in the downward direction gives you weight. For the different kinds of forces, there are a bunch. I'm going to use different letters. They're not all going to be F. The individual kinds of forces will have different letters. And the total force, I'll say F net. I'm going to try to do that uniformly, consistently, everywhere. My hope is that will help avoid the tendency to say F equals negative mg and plug that into ma. Hey, by the way, when the only force acting on you is your weight, what do we call that? Free fall? That's how I defined free fall. Let's plug this weight formula in to F net over mass equals acceleration and discover what we can. What is the force then? If the only force is weight, shove that sucker in there. Negative mg divided by m equals acceleration. What have I discovered? M cancels m. Oh my sweet baby Newton. Acceleration is downward with magnitude 9.8 meters per second per second. See? Actually, you could reason backwards from this to find the mg formula, negative mg formula. There is a second formula I'm going to give you. Support force or normal force let me make a brief note before telling you the formula. Normal in physics has nothing to do with regular, usual, typical. Normal does not always apply. Put a note in your notes to that. There's not always a normal. There is not always a normal. Normal does not mean common. Normal, in fact, means at right angles, perpendicular. Right now, this tabletop is horizontal, right? which direction is the force it's exerting on the ball? Vertical. That is at right angles to horizontal. Hey! That's what it means to have a normal in physics. What happens if I tilt the table? The ball rolls. Did gravity change direction? Did gravity suddenly start pulling sideways? Did anyone feel pulled that way? No. When I tilted the table, normal force at right angles to the surface started pushing a little bit out, a little bit up, and a little bit left, from your perspective right. It was normal force that actually caused that ball to roll. If you took away weight, if weight didn't exist, I'm not claiming the same thing would happen. You go into outer space, you do that, nothing's going to happen. Okay, but the force that actually pushed you over, pushed it down the ramp, is at right angles to the surface, partly pushing it downhill, partly pushing it from your perspective right. That's the thing that actually accelerated the ball. The equation for normal force, and then I'm going to let you go, I swear, is there is no equation. This is a very common goof. We're going to be using normal forces left, right, and center. I mean, normal doesn't mean common, but it is common to have normal forces. And you will discover normal force in each time based on reasoning. I want you to know there's no equation that you plug in. This is something you have to brain about. I will take questions if you come on up. Otherwise, you are all excused. Today, everyone gets 100 on participation because I can't. Or maybe I'll just, I don't know. Yeah, whatever. Everyone gets 100. Try